BioVivacious. As you know, BioVivacious is a YouTube channel dedicated to clearing fundamental concepts of biosciences. Today we are going to deal with one of the most fascinating subjects in biosciences. That is how exactly ATP molecules are synthesized. Now in ATP synthesizing, we first of all look at the structure of this particular enzyme which is synthesizing ATP, whose name is the F0 F1 ATPase. Then we shall subsequently we will look at the synthesis of ATP. You look at the past history, roughly about almost 70 years, maybe accurately speaking, it all began in 1940s. Scientists have been very curious to know how ATP molecules are synthesized. So they began experimenting. We need to know about two very, very important scientists. One was Peter Michel, with his very sound theoretical knowledge, and all the kinetic studies carried out by Paul Boyer. The contributions of these two people, these two scientists, is so significant to our understanding of ATP. So let us begin with the structure of ATP for this ATPase enzyme. There is a very huge problem in synthesizing ATP. The problem is, if you look at ADP, let us consider ADP is 2 minus and inorganic phosphate is just 1 minus, okay, monoanionic species. We have to bring these two molecules closer in order to produce an ATP molecules that is again 3 minus. So it will overcome, we need to overcome this Coulombic repulsion. A condensation reaction has to occur, a molecule of water has to be released, then only ATP synthesis can occur. It is a huge task, and all these must happen in the inner mitochondrial membrane. How is this huge task achieved? 70 or 75 years of experiment, and what we are going to see today is the result of that experiment, whatever we know as of now. First of all, let us look at the structure of this complex. Now if you look at this complex, as the name suggests, it has two portions. One is called an F0 portion. F0 is hydrophobic and F1 is a hydrophilic. So therefore the enzyme has a hydrophobic and a hydrophilic region. Now let us first begin by looking at the hydrophilic region, that is the F1 complex. Now the F1 complex, now understand the location. If this is the mitochondria and this is the inner membrane, okay, and this is the outer membrane, this unit is located here. Here will be the F0 and here will be the F1 complex. So this is how it is located, and so far we have learned that H plus ions are present in the inner mitochondrial membrane. So we have been seeing it in the last 4 complexes. The function of the 4 complexes is to pump or create a proton motive force in the inner mitochondrial space. So it is made. Now we are going to allow these molecules to come inside in order to make ATP molecules. In the process, what will happen is ADP will join together to form an ATP to overcome the Coulombic repulsion. This is the summary. So therefore, let us begin by looking at the structure of F0 complex. I read a very fascinating story in a journal about the structure of F1 and F0 complex. Now I felt that this is an excellent analogy. That analogy is all about an orange. Okay, so an orange this portion we are going to consider with the structure of the F1 complex. When you peel the orange, peeled orange, in the different segments you can see in an orange. So let us consider that each of these segments is a portion of the F1 complex. Now, these segments, assume there are 6 segments in this orange. Now, these segments, we shall call them alpha and beta subunits. So, therefore, here is an alpha subunit. So, they are alternately arranged. After an alpha subunit, there is a beta subunit. This side also there is a beta subunit. Now there is an alpha subunit. Here also there is an alpha subunit, and here there is a beta subunit. So therefore I am writing, so this is an alpha subunit, this is a beta subunit, this is a beta subunit. Therefore, there are 3 alpha subunits and 3 beta subunits. Okay, so therefore in the F1 complex, 3 alpha and 3 beta subunits. Now this is our orange. What more is present in our orange? Assume that this orange is located on a pencil. So this is very significant. So we are allowing this pencil to pass through. So therefore this orange is located on this pencil. Let us call this pencil as the gamma subunit. So the pencil is the gamma subunit. I'll use a different color. This is the gamma subunit. Okay, there is only one gamma subunit. So we write that. Now there is a possibility that this can slip. So there is an epsilon subunit which is attached to this. So therefore the epsilon subunit is here. So we are missing a delta subunit. Now currently let us put the delta subunit here. This is the delta subunit. So therefore, if the configuration of the F1 complex is alpha 3, beta 3, gamma 1, delta 1 and epsilon 1. This is the configuration of F1 complex. If the molecular weights are, this is about 55 kilodalton, this is 50 kilodalton, 31 kilodalton, 19 kilodalton and 14 kilodaltons. So these are the molecular weights of these particular subunit. Okay, so therefore this is how in the orange and the arrangement on the pencil looks like the F1 complex. Now let us look at the F0 complex. Remember, F0 complex is the hydrophobic region which is there in the inner membrane, anchored in the inner membrane. F0 complex has got 3 components. In the 3 components, let us call them A, B and C. There is only one A. There are 2 B's and C's. It can be 9 to 12 C subunits. And their molecular weights are, this is about 30, this is about 19 and this is about 8. So this is the structure of the F0 or the hydrophobic region. What kind of an analogy we can give to the hydrophobic region? So I am sure that when you move around in the city, in the shopping complexes, you would have seen that people making a floor with using a huge grinder. So there is a huge grinder that will keep on rotating. Get that image of that grinder. So that thing which is rotating is in the C subunit. Remember, the C subunit is basically alpha helical protein. About 9 to 12 alpha helical protein, it becomes that huge drum. So therefore, if the huge drum is this way, this is the huge drum. Okay, this is the C subunit. Now remember, there can be 9 to 12 such alpha helical transmembrane proteins. So therefore, we denote it this way. Each E1 is a subunit. Okay, each one is a subunit. So therefore, each one is a subunit. You can visualize it. Now, in the so that is C. In the A subunit, okay, assume that the same experiment of the drum. After some time, the drum has been rotating for long hours. It gets heated up. What normally the shopkeeper does is he will take a cloth, a wet cloth, and he will keep around it. So the drum will keep moving, and his hand will be stable there, giving cold press with the cloth, so that there is a possibility that the drum can cool down. So this hand which is pressing the drum is our A subunit. So remember, there is only one A subunit, so therefore we denote the A subunit in the following manner. This is our A subunit. Okay, this is our A subunit. Now what is left? Only the B subunit is left. There are two B subunits, and the B subunits will connect the A subunit with the orange and with the help of the delta subunit. So therefore this is one of the B subunit, this is B1, and this is the second B2. So you can see that how this arrangement occurs. Let us also complete this by drawing the membrane. So the plasma membrane, that is either membrane or the inner mitochondrial membrane, will be like this. Use a different color so that okay, this is the membrane. So therefore this is the membrane, and this portion is going to be matrix, and this portion is going to be in the inner membrane space. Okay, this is the matrix, this is the inner membrane where H plus ions are present. If the diameter of this orange is about 10 nanometer, that is the diameter. So this is the basic structure. So therefore this is the F1 and this is the F0 region. Okay, now this complex is a rotary enzyme. This is an example of a rotary enzyme. That means an enzyme that can rotate. What all can rotate? The C can rotate, alpha can rotate, C can rotate, gamma can rotate, and the epsilon can rotate. C, gamma, and epsilon can rotate. All other components, that is the alpha, beta, delta, B, A, they are non-rotatory or stationary portion of this enzyme. That is very important. Now what happens? In order to understand, once this structure is clear, in order to understand this mechanism, let us look very closely at the C subunit. So I'm drawing a structure here, keeping this here in mind. So in the C subunit, okay, so this is the A subunit. So look at the A subunit. What is important about the A subunit is it has two half channels. What is the meaning of half channels? It means it opens only from one side. That is the meaning of a half channel. So therefore it opens from here. It opens here and the half channel ends there. The other half channel is aligned to this and opens to the other side. You see the beauty of this structure. Okay, it opens from here and it ends here, it is blocked. Whereas it opens from the other side and it is open to the matrix side. So there is no direct connection, but yet there is an indirect connection. That is the point to be noted. Something which is very, very fascinating about this structure is in the C subunit. In the C subunit, we have seen that there are 9 to 12 C subunits. In the C subunit, the 61st amino acid is so crucial. That is an aspartic acid. So, in the 61st aspartic acid, 61, which is very crucial. So, therefore, in each of the C subunit, there will be aspartic acid 61. And that is aligned with this, in the half channels. So, therefore, let us denote the half channels within the structure. So, denoting it here. So, these are the half channels. Okay. Half channels, and these half channels are aligned to an aspartic acid 61. So, therefore, there will be 9 to 12 aspartic acid. What is also important is this aspartic acid, as you know, it's an acid. So, therefore, aspartic acid COOH, this can ionize in the pH of the membrane and it will stay as aspartate and H+. Okay, it can ionize. Now, the point to be noted is out of this 12, 9 to 12, except one will stay in this form, ionized form. All the others will be in its acidic form. One will be in ionized form, all the others will be in the non-ionized in the acidic form. Okay, so this is the background that we need to understand in the pumping back of protons. In earlier sessions, we have seen that complex number 1, 2, 3 and 4, their main purpose is to transport protons across the membrane. If you had seen an earlier diagram, so we have seen that in the inner membrane space, lot of protons are pumped to that space. So therefore, it is creating a proton motive force as well as a membrane potential, a potential difference it is creating. So therefore, these H+ ions are so enthusiastic, they want to come back to the matrix side. So the H+ is struggling to come back to the matrix side. So therefore, now let us see what happens. This H+ ion, one H+ ion comes inside. So it can come only up to this point. Now assume that where it is matching, it is exactly aligned with the aspartate 61. It is well aligned with the aspartate 61. So what is likely to happen? So therefore, here is the aspartate 61. Aspartate 61. Okay, it is ionized. So here comes an H+ from the inner membrane space, and this will become COOH. So it becomes an aspartic acid. When it becomes an aspartic acid, so the whole equation changes. What will happen is, now there are 12 C subunits. Okay, now this becomes aspartic acid, and if this is the first one, now the last to the first one, that is the 12th one, that will donate a proton. That will donate a proton to the membrane's matrix side, facilitated by a glutamic acid 196. It will transport a proton. So, in other words, a proton comes here, another proton is transported back into the mitochondrial matrix. So now this will give a push, a torsion to the C subunit. So the C subunit will rotate in this direction, anti-clockwise. So the C unit is rotating in the anti-clockwise, which means, remember, what all are attached to C subunits? In the gamma and in the epsilon. So in the gamma and the epsilon, now gamma and this is the C subunit, assume. This C subunit is rotating the pencil inside the orange. Remember, the pencil is now rotating, being rotated inside the orange. This is the point to be noted at the moment. So we will take up what happens to this orange if there is a rotation happening. If energy is transferred, what happens? We will look at that next. So I am sure that you have got the picture about how the transfer of protons, how the proton motive force is used, and how protons are pumped back into the mitochondrial matrix. So this process will keep on happening. And this is how protons are transported back into the mitochondrial matrix. I am sure that you have enjoyed this session in understanding, in conceiving the concept of the proton transfer back into the mitochondrial matrix. And this is, in a way, we are making an effort to understand how exactly ATP synthesis occurs. Keep watching this channel. I am sure you will enjoy that.